Alright, so we're in section 12.3. We're going to talk about velocity and acceleration. And the idea here, what we're doing is we're going to take what we know about vector valued functions, and we're going to use that to describe motion in the plane or motion in space. So we're letting our vector valued functions represent, our vector valued function represent position, and we're thinking of our parameter as time. So we're saying that r of t is some function x of ti, gives our x component, plus y of tj for our y component, and z of t k, and time is our parameter. So r of t would describe the position vector, and our position vector changes with time. So if we think about a vector valued function this way, then r prime is going to be our velocity vector. And we could write v of t, and v of t is going to be our velocity vector, is going to be tangent to r of t at time t. So our velocity vector is tangent to the curve described by our position vector. And if we differentiate again, our double prime is going to be our acceleration. And we usually write a of t for our acceleration. And the speed is the magnitude of the velocity. So that's going to be the magnitude of our prime of t. And the scalar acceleration is just the magnitude of our acceleration vector. So everything that we're doing in this section has to do with interpreting our vector value function as a position function and applying what we know about position, velocity, and acceleration to these vector value functions. Now, the most classic example of velocity and acceleration with vector value functions is projectile motion. So that's what we're going to talk about next. So for projectile motion, we're thinking of projectile motion close to the surface of the Earth. We're making some assumptions. So our assumptions, to simplify our work, is we're close enough to the surface of the Earth that we're saying that the Earth is flat. So we're not talking about we're not taking into consideration the curvature of the surface of the Earth. We're talking about a flat surface. We're close to the surface of the Earth. So we're being close to the surface of the Earth also gives us the simplification that the force due to gravity is constant. So our force isn't varying as we move around. We're not going far enough away that our force varies. And gravity is the only force that's acting on our projectile. So we're not taking into account any kind of friction, any kind of drag, anything else. So these are assumptions that help us out, that simplify our calculations. So our diagram, we'll draw a diagram here we're going to use to come up with our equations. So we're draw our axes, so we're having a y and an x. Our projectile is starting from some point x0, y0. It's starting off with some initial velocity. So this is our initial velocity vector v0. It's being launched at an angle theta from the horizontal. So there's our diagram. So given these assumptions, we can say that our acceleration vector, our double prime of t, is minus J. And G is the acceleration due to gravity. And our acceleration due to gravity, we're saying G is, our force is negative, so our force is acting downwards. And our acceleration due to gravity depends on our units. In imperial units, it's negative 32 feet per second squared. In metric, negative 9.8 meters per second squared. So G is our constant acceleration due to gravity. We're going to say that our initial position, r of 0, is the position vector x0, y0. And r prime of 0 is just our initial velocity vector, v0. And we can, given this angle from the horizontal, we can say that v0 equals the vector, the magnitude of v0 cosine theta I. So that gives me my x components, gives us our x component of our initial velocity, and the magnitude of v0 times the sine of theta, j. So that gives me the y component of our initial velocity. So that's our initial velocity vector. So we're going to integrate once. So we're going to start with our double prime, and we're going to integrate once to get going to do one integration, and we get that r prime is minus gt j plus, and we have a constant of integration, and our constant of integration is a vector, plus c1. We plug in t equals 0, our initial condition, at time equals 0, and we get solve for C1, and this tells us that C1, our constant of integration, our vector constant of integration, equals our initial velocity. I'm just substituting time equals 0. So C1 is going to be our initial velocity. So I can write, substituting our initial velocity in, I get that R prime, or substituting our quantities in, R prime is, and I'm going to just fix my notation here, there we go, our double prime. Our prime is minus GTI. Sorry, I went one step back, I'm copying the line before. R prime is going to be V0, magnitude of V0, cosine theta I, plus the quantity. So I'm using my initial velocity here and my expression for initial velocity. Magnitude of V0 sine theta minus GT, and that's going to be in the J direction. So at any given time, this is going to be my expression for the velocity. One thing that's important to remember in projectile motion, the x component of the velocity, we can see here the x component of the velocity doesn't change. So whatever the x component of the velocity is initially, that's going to be the x component of the velocity throughout the course of motion. Because the only force that's acting is gravity, the velocity only changes in the y direction. So only the y component of the velocity changes. So I'm going to integrate another time. So I'm going to integrate r prime. So our second integration gives that our position vector, r of t, is the magnitude of V0 cosine theta times t I plus, and I get a little more complicated expression for the y component, magnitude of V0 sine theta t minus gt squared over 2 j plus my second constant, vector constant of integration. So I'm just integrating the velocity to get my position. I'm going to substitute t equals 0 to find that my second constant of integration is my initial position vector. So I'm just using the initial condition. We know that at time equals 0, my position is x0, y0. So I'm substituting time equals 0 here, and I find that my second constant of integration is just my initial position vector. So finally, I'll substitute this expression in and combine like terms here, combine my components to come up with my expression for my position vector. So r of t for projectile motion is x0 plus the quantity magnitude of V0 cosine theta t, that's my I component, and my j component, I have my initial y position, y0 plus the quantity, magnitude of V0, sine theta, t minus gt squared over 2, and that's my J component. And usually, just kind of common usage, we say that it makes our problem easier if we say that x0 equals 0 and y0 is, we call h0 our initial height. So that's, you'll see that often in these expressions also, that y0 is our initial height. And if you set your x0 at 0, you just have to remember if your initial position isn't at x equals 0, just remember you're shifting your entire function over by that particular amount. So this is our kind of our classic expression for projectile motion near the surface of the Earth, with the assumptions that we're close enough that the surface of the Earth is flat, and that gravity is the only force that's acting on our projectile. And in class, what we're going to do in class is, when you walk in, there'll be some problems on the board that have to do with projectile motion, have to do with velocity and acceleration. So the first part of the class is going to be spent working those problems and talking about their solutions. And then the homework is just involves velocity and acceleration and projectile motion.